Hello, everybody. Welcome to Carnegie Mellon. I guess it's the first day of the new semester. It's a real pleasure to be able to see you all. There are some people who are randomly watching this on YouTube, so hello to all of you. Don't worry to anyone in the class, you are not being broadcasted on YouTube. I just have the exact camera feed that I'm sending into this room just flying onto YouTube because some people want to know what's going on. But let me also make sure I'm loud enough. I just want to double check the audio levels for the Carnegie Mellon. That's what we're focusing on. Is this audible or is it too quiet? It's good? Okay, we're going to keep it like this. Right, so this is the class on discrete mathematics, and so we're going to be talking about all kinds of things that you can do if you just have some discrete objects. What does that mean? Well, they could be in the form of counting numbers of ways to do things. That's often called combinatorics. But you can also think about networks. And in fact, actually, if any of you are following the work that I am working on nowadays to try to stop COVID, these ideas about networks can be extremely useful. In this class, we're going to run across a lot of these different topics. Now, the way I like to run these kinds of classes is I have this. I actually can see 25 of you in this Zoom classroom. So that's just what I have in front of me here. My vision is not really good. So when it comes to reading the chat, to me, the chat is very small and very far away. So the way, if any of you took a class with me last semester, the way I like to run this is that if you want to answer a question or say something, you type into the chat, raise hand. And some of the other people in the other class figured out that RH does the same thing as raise hand. But we want to feel sort of like a normal class. So the way this will work is if I ask some kinds of questions, just like type raise hand or RH into the chat, and then I'll call on you, and then you'll say what you were going to say. I respect the fact that not everyone is able to turn their camera on and turn their microphone on. That's the reality of our world. But what I will say is, if you are in a position where you can, I'm just going to give a random feedback that if you do, you'll probably have a bit more fun because then the class will seem a bit more like you're learning with people as opposed to learning with white text on black screens. So it could feel a little bit more fun. And I'm also going to give you another very practical advice. It might not be useful for my class, just depends on your situation. But I mean, recently I actually got some requests for letters of recommendation. And the sort of feedback I gave to the people was, I can definitely write about how you did in my class if you have some exam scores or homework scores. But it ends up being a whole lot easier to say more than just this person took the class and got this many points if I have some idea of who you are, what you're doing, what you're saying. So I just wanted to give the random feedback that not just for this class, but for any class you're taking, if you actually participate more, it can actually be helpful for you long term. So that's just a feedback. Okay, well, I'm supposed to say something about how the class is graded and all of these things. So let's quickly get through all of that part. There is actually a course website. I finally put it up about 15 minutes ago. We happen to have this Canvas page too. Oh yeah, somebody messaged me last night saying, when is the course link going to be up? And I was like, that's a long way away. This is the sort of things that I'm working on these days. A lot happens in the course of 3 hours. But so it did happen. We got it done. The course website is up. I'm using Canvas. Canvas is going to be able to have these assignments. I believe you submit your assignments through Canvas. We have 3 amazing TAs who are going to be helping to grade all of these. And because I'm a bit old school, I also made an old-fashioned course website. That's an HTML website. I guess the easiest way to get to that is I'll post a link to that in the Canvas. If you're curious, where we're going, that kind of shows out the syllabus. And some information from that website. It will show that there's actually no real textbook for this class. There is a book that is actually quite good. It's a book I mentioned on the course website. It's called, I think, Discrete Mathematics. And it's actually a very good book. If you're curious, you're welcome to read it. But what I've learned over time is that the Carnegie Mellon audience is quite advanced. So we actually go quite a bit beyond that book. You guys are actually in luck. In the past, there was not a real textbook for this course. But 2 years ago, there was an incredible student named Nathan Moss who took notes so detailed that about a week after the class, he said, "Hey, I made these notes. Do you want them to do something with?" And I was like, "What's this?" So some student sent me a PDF file. What is this? I opened the PDF file. It's 120 pages. And it has all of the details of everything that happened. And I said, "This is incredible. I've never seen anything like this in my life. Let's write a book about this." So actually, there is a course textbook. It is the course textbook that was co-written by a student who took it 2 years ago. But I'm not going to give the whole book to you guys in one shot because that's no fun. That's like getting to know what's going to happen in the movie before the movie happens. So what I'm going to do with this is like after each week or so, we can share, the part of the book that corresponded to that, part of the class. Okay, that way we can keep the suspense up. Right, other things. So there's some grading that we have to do. So the way that the course grading works is homework is 10%. There's actually already a homework assignment I put up onto Canvas. It's just to, I guess, to get our wheels rolling. I'm not sure what the phrase is, but just like get started for the semester. So there are 4 questions. That one's due on Friday. And the homework is worth 10% of the class grade. I strongly recommend that you talk to other people about the homework. Collaborate all you want. The past history of this course, a lot of the people who have taken it before have said that the homework questions can be deceptively hard. And even though there are only 5 questions every 2 weeks in the usual way, this first week is different, but usually there's 5 questions every 2 weeks. Don't wait until the last day to do it because they're actually quite hard. A lot of people like to get groups of other students together and think about them together. So that's how homework works. All I care about is that when you submit your solutions, they are things that you actually did the typing on or the handwriting on. Don't just grab someone else's tech file. There's also exams. Exams are 60%, so there's 90% left, right? So it's 60% through the midterms. There are 3 midterms. And there is also one final exam, which is 30%. And this is written on the course website. So the way the exams will work, it's quite hard to do all of this in a reasonable way with online. But the way we always did it in the past was we did all the exams in class. And so there are particular class dates also on the website. Thank you so much, Chris. So Chris is the sleuth who has found the course website. Good for you. So that's the course website. And the exams, they are split through the semester. The course website actually says exactly when they are. Approximately like the midterms are like 1/3 of the way in, 2/3 of the way in, almost 3/3 of the way in. And they are all like 50-minute exams. The structure of the exams, just so you know, they are all open notes. They are all open book. I'm not exactly sure how to deal with like open notesness if you take notes online, because it's not great if you're just like Googling how to do it. So I think what I'm going to say about the open notes part is I would prefer if you use the open notes type thing, you actually use something that is not on the screen. This is the annoying thing about having to proctor exams online. And just to make it clear, I want to talk through all of this part so everyone knows what the exam policy is, because that's what we always have to do with online teaching. Honestly, I wish it wasn't this way, but unfortunately, because the only thing we can do to proctor is to have everyone join Zoom, the exam policy is just you would need to be on Zoom, you would need to have your camera on, you need to be able to be, far enough away from the computer that it's clear you're not just like constantly writing on the computer. And what I will do is I'll give out the questions. The questions can be a PDF that you can have on the screen. And I'm okay with you, I guess, going to the computer, looking at that thing. But ideally, don't be so close to the computer that you could just be like typing and looking stuff up all the time. We do have to trust people. So in some sense, a lot of this is also going to be based on trust, and whatever we can monitor, we'll monitor. But that will also help make it fairer for everybody else, because it's no fun if some people are not playing fair, if that makes sense. The good news is that the questions are actually always original. If you ask anyone who's taken my class before, what they will tell you is that you never quite know what kind of question is going to be on the exam, because I will always give you all the questions that I've ever given before on previous exams. And that's just a guarantee that none of the questions on today's exam will have anything to do with any of those. So it's just that the principle of the class is learn how to think. Generally speaking, there have been questions on the exams that you wouldn't even be able to Google. So that helps to make things a bit more fair. But just to make sure that people know the ground rules, we will need that people are taking the exam on Zoom. I'm respectful of different time zones. So I've actually set up an alternative time. If people cannot make the main time, there's an alternative time with totally different questions that will allow to cover these 2 ends of the time zones. Okay, and then there will be a final exam. The final exam will be run whichever way the registrar, whenever the registrar schedules it. I think that's mainly the situation with grades. Oh yeah, people often ask like, what's involved? How do you get an A in this class? The website actually does say that in the past the threshold for an A was like fairly low. That's because the exams are hard, and that's fine. I mean, it's designed in a way so that they're actually interesting. There's not really gimme questions. It's more of let's see how everyone can think. But generally speaking, people have been quite happy in that when they worked hard. They figured it out. Actually, I don't remember what the 66% was. I'm not sure if it said 66% got an A or whatever. But in general, I basically look at what people are able to solve, and generally speaking, I'm very impressed by what people figure out by the end of the course. Okay, questions. So Chris, I see you posted something that I can't read. I know that you posted a link, so I guessed what that was. What was the other thing you posted? I can sort of read. Something about like the historically cutoff for A has been around 60% of the total points. Excellent. I mean, my main advice is just like if you pay attention and think and actually work on the homework and also work on the past exam problems, you'll be fine. And you will learn a whole lot through this. Are there any other questions about the grading stuff? If you want to ask anything, feel free to like type raise hand or even jump in. Okay. Well, if not, let's go ahead and do some math. So what I'm going to do is I'm going to just dive right in and start talking about combinatorics. And a lot of times when people think about combinatorics, they think of like counting how many ways there are to do something. So since this is the first class of the whole semester, let's go over there. And for this first class of the whole semester, I want to make sure I can see you. And I want to start by talking about some questions that will move from pretty standard to maybe not so standard. So the first question, and that's actually how I like to teach. I like to teach by posing questions and let's have people suggest answers, right? So let's start by doing some counting. And here's the first question. How many 4-digit numbers are there? Anyone want to jump out and say something? Just type raise hand or RH or something. Let's make it more fun. And don't worry, they'll get harder. Okay, let's go with, I need to read. Charlie. I just realized something. Now I know why I can't hear you guys. I had my volume down to 0. Charlie, can you say it again?
You would do 10 choose 1 for each digit, so it would be 10 to the 4th.
Okay, so what you said is you got 4 digits, okay? And you've got these 4 digits here. And each of those 4 digits has 10 choices. And if you have 10 choices for each of those digits, then the answer is 10 choices for the first one times 10 choices for the second one times 10 choices for the third one times 10 choices for the fourth one. Okay? That's a legitimate answer based on how one could interpret this question. Okay? And I see that there's another idea. Tim, is that you? Obviously, I can't read. Was that a Tim? Oh, that is a Tim. Okay, well, I'll echo what Tim said. Tim said, doesn't the first digit have only 9 choices? It depends how you interpret the problem, right? So if you interpreted the problem to say it's a combination lock, this is the answer. If you interpreted the problem to say, let's be more clear now, I'll write where the first digit is non-zero. If you go and add that piece and say the first digit has to be non-zero, suddenly your answer changes. Suddenly your answer changes to not 10 choices anymore, but 9 choices. Because the first digit can be 1 through 9, right? So it's 9 times 10 times 10 times 10. So this is the basic multiplication principle. And the reason why it works, I mean, a lot of times we just memorize this or know that that's how you do this problem. The reason this works, by the way, is because no matter what you do for the first digit, there are 9 choices for the first digit, and no matter what you do with that first digit, there are always 10 choices for the second digit. I'm just writing this out. Even though a lot of people know how to do these kinds of questions, I want to emphasize the logic because we're going to twist it soon. So the question here is why times? It's actually since no matter what you do for the first digit, you always have 10 choices for the second. And since you always have 10 choices, that's why you multiply by the 10. That was the first question. Second question, I want to just go and twist this a little bit and say, how many 4-digit numbers are there where the first digit is non-zero and also there's no two equal digits next to each other? How many 4-digit numbers have the first digit non-zero and no two same digits next to each other? Okay, I see some hands. Venkatesh.
Yeah, it would be 9 to the 4th because the first digit has 9 choices, so it's non-zero, and then the second one can be anything except for that. So there's another 9, and same for the third, and same for the fourth.
Okay, so I want to talk through this because this is a little bit interesting of the order suddenly matters. So what you said is that there are 9 choices for the first. That's true. Sorry? Yep, that's true because it could be 1 through 9. But then the important thing, notice why I emphasize this thing about no matter what you picked for the first one, there are always 9 choices for the next one that just avoid copycatting what you got before. Okay, so that's the important thing. No matter what you did for the first, you always have 9 choices from 0 to 9. That's 10 choices, but which do not copycat the first. Which do not copy the first. Right? Because I can't have 2 of the same digits next to each other. So that's 9 choices. And then the nice thing is this keeps going. If I just go and look on the next one here, well, here I would have 10 choices, 0 through 9, but there's exactly 1 digit to avoid, which is the one right there. Did that make sense? So the important thing is, why is it always 9? It's because, well, the first one's weird. It's because you just avoid 0. And then all the rest of them, it's you have any of the 10 digits except the one that happened right before it. So here's also 9 choices for the same reason. And the same here is like also 9. So the answer is just 9 times 9 times 9 times 9, which I'm actually not very keen on arithmetic. That's good enough for me. 9 times 9 times 9 times 9. Okay, why did I do this? It's because I wanted to emphasize there's a very important thing that he did when he was solving this problem, which is to start from the left. What would happen if you started from the right? Aha, out of it.
You might go around doing a similar thing, but then you encounter problems when you get to the first digit.
Yeah, so why not start, yep, from the right? And I just wanted to emphasize, like, sometimes things are asymmetric. Sometimes the order matters. Actually, as a mathematician, I go through life looking at the world, trying to figure out when there's something where the order matters. And if you ever find out something where the order does matter, you have an opportunity to do something different. So if you tried to go the other way, if you did this first, if start here, actually, how many choices do I have if I just say start there? How many choices are there for that last digit? Well, it's 10. Yes, thank you. It's 10 choices because 0 through 9, all legit. You have 0 through 9, so 10 choices. And so far, so good. You know, there's 10 choices there. Now, if you go here next, what you could say is, well, here I have, I did whatever I did. And actually, no matter what I did there, if I'm now filling in this second last digit, I choose from 0 through 9, and I just have to avoid that one over there that I used. I'm saying that 9 is a legitimate idea for no matter what I've done for the first choice, I always have 9 ways I could continue. I'm emphasizing it looks okay for a while. So here, no matter what you did, for the last digit, you have 0.9 without that digit as 9 choices. But now if I keep going with this logic, it's 10 choices, 9 choices, and then here on the third to the right, or the second from the left, here you also have 9 choices. But then what is the problem over here on the leftmost digit? This is what Adabate was talking about. Yes, raise hand, Braden.
Well, you're going to have a different number of options for the first digit, depending on whether or not the second digit is 0.
Yes, number of options will depend on whether hundreds digit is 0. If it is, if the hundreds digit was 0, I'm actually working this all out because we're about to get an inequality, which is also useful. So if we actually had that the hundreds digit was a 0, how many choices would you have to put something here for which it's different from the digit next to it? If there was already a 0 here, 9. Is that right? 9? I think so. I think it's 9. Yeah. If you had a 0 here, then you could use any of the digits 1 through 9, and they would all be legit because you don't have a 0 in front. That was the rule. And it's not equal to the one next to it. So if it is, you have 9 choices. And if it's not, how many choices do I have if it turns out this was not 0? Then it's 8, right? Because if this is not 0, it's one of the 1 through 9. It's one of my options, so I lose one of my options. So I have 8 choices. Okay, and what this actually shows you is it shows you an inequality. It tells you that the answer is 10 times 9 times 9 times something between 8 and 9, if that makes sense. Specifically, what this is showing you is so the answer is between 8, well, let's write it in the order that we did. 10 times 9 times 9 times 8, and 10 times 9 times 9 times 9. And it is. Actually, if you look at 9 to the power 4 and take away the common factors, we're basically comparing 10 times 8 versus a 9 times 9 versus a 10 times 9. And it is in between. So this is just showing you that sometimes, if you do it the way that doesn't give you an exact answer, you can still get an inequality. And that's actually something we often think about in combinatorics too. That leaves us enough time to go and play with the next question. The next question is quite surprising. So now I want to know how many 4-digit numbers there are. How many 4-digit numbers are even? Well, let's skip all the way. So not just even, I'm going to say are even, and also don't have any 2 same digits next to each other. And have no 2 same digits next to each other. And I just want to emphasize for this question, to make it more interesting, these 4-digit numbers not starting with 0. Okay? I don't expect an answer. In fact, please, if you know the answer, don't give it away. That will spoil the fun. I know actually that the background experience of the people in this class varies widely. We have some people here who did a ton of math competitions before. We have some people here who didn't. And there's nothing wrong with that. My goal here is to bring everyone along. So if you actually already see through how to solve this, don't give it away to everyone else. This is actually quite interesting. But let's puzzle through this together. How might you try to approach this? I don't need to have a complete solution. I just want to know, try something, and if it doesn't work, we'll figure out where and why. And I actually expect a bunch of things don't work. If you have an idea that doesn't work, let me know too. Ooh, okay. Ihsane? Did I pronounce your name right? Ihsane?
Yeah.
Ihsane? Yes.
So I was thinking about like the last digit. So in order to be even, we have like 5 choices for the last digit.
Okay, good. So let's start brainstorming this together. You have 5 choices here. That is true. And by the way I teach my class, totally okay to be like, here's one idea, and then everyone else goes on. Thank you, Ihsane. Now what? Anyone can like build onto this. Ben San.
Okay, so I was thinking like, if you have 5 choices for the last digit, and then you can figure out the number of 2-digit like numbers, and then subtract the number of like 2-digit numbers that have digits.
Ah, just a second. So you want to use like some subtraction method. Are you saying like, I could get this answer by figuring out how many of them... are you saying how many 4-digit numbers are there that are even, and then subtract away the ones that have 2 repeating digits? Is that what you were saying?
Oh no, I was yeah, basically that.
Okay, and I heard you say something about 2 digits, of like try it on a smaller problem. All these ideas are very interesting. I'm going to put another answer here of like, well, another way to do this is we could just count the number of 4-digit even numbers. And Ihsane's idea would work actually quite well for that, because that's going to be nice for multiplying. 4-digit evens. And then you could subtract the number with same digits next to each other. Okay, this is cool. More ideas. This is supposed to be not easy, by the way. This is intentionally supposed to be not easy. And if people have ideas of like, I'd like to do this, this, and this, but it looks like there's a challenge, I'm also interested in you suggesting that. Because that will help everyone be like, okay, what's hard about this? Like, why is this not like, bam? Ooh. Martine. Okay, in between. Okay. Let's do this. Actually, let's do both of these, because what I'm seeing is that Ihsane's idea is gonna go from, what does that mean? What's left and right? I don't know. From like this side to that side. Ihsane's way goes this way, and you're going the other way. And it's like let's get as much information as we can, right? So your idea was to go the other way, and actually I want to do both of them. Okay, so Martine was your name, right? Yeah, Martine. So you're like, the first one has 9 digits. Okay, 9 choices. I'm not writing as many words because unfortunately I don't have 3 blackboards. I love teaching at CMU where we have all these blackboards. Here I've got one tiny screen. But this is 9 choices for the first. Let's continue. Martine, how many choices for each of the other ones? Can you help me out?
Yeah, you have 9 for the 100 as well.
Okay.
And 9 for the 10.
And then it becomes weird. What's this?
And then depending on whether or not this is even, if the 10th digit is even or odd, you'll have 4 or 5 choices.
Excellent. Are people following what's going on here? I mean, I sort of just wrote a lot of little tiny scratch notes, but it's like 9 choices for the first because it's 1 through 9. And then it's like, okay, avoid that 0 through 9, but avoid the one you saw. So, okay, times 9. Then take 0 through 9, but avoid the one next to it. 9 choices. And then suddenly you've got to be even. So it's like 0, 2, 4, 6, 8. So 5 choices. Except if you had an even one already used over there, it's only 4 choices. Okay? So what you're finding out is that the answer is between 9 cubed times 4 and 9 cubed times 5. Okay? But now let's go to Ihsane's thing, because we can do that too. right? So let's try to go the other way with the same thing. Got 5, and if that was 5, how does this go? 5 and then 9 choices, right? Because it's like I choose anything here that avoids what I already chose there on the last one. So 9 choices is okay. 9 choices. And then I'm just like going backwards. So this is like another 9. But then what's the deal here? I didn't see if if anyone just typed. Okay, other bit.
That would depend on whether the 100 student is 0 again.
Yep. So what is that, 8 or 9?
Yeah, 8 or 9.
We saw that already. Okay. So now we
Oh, never mind.
okay, let me just write this down first. So then what we got now, we got another thing. Answer is between, we have an 8 times 9 times 9 times 5, and 9 times 9 times 9 times 5. Okay. That's kind of cool. Actually, what are these? So I don't have a calculator on me. I'm not very fast. Can anyone help me work these out? We got like 4 numbers here which are like multiplied stuff. Somebody's Discord is ringing. Awesome. That's okay. So like back to actually when I heard that I was like, is my Discord ringing? But it's okay. It's okay. This is the world we live in now. So help me with these numbers. What are they? Did anyone do the? Don't worry. Did anyone do the calculation? Because I want to look at them. Okay. So for the bottom, 2916 to 3645. 2916 3645. I hope that's what you said. And for the top, 3240 to 3645. 3240. Okay. Interesting. So what is this? We happen to have both of them have 3645. Okay. But if I use the two together, it looks actually like the top one is like tighter bounds. Okay. So we now know the answer is somewhere between this and this green numbers. But what is it exactly? So when we look at a question like this, it can be useful to say, this is irritating. I can't go from the right and I can't go from the left. Now what am I supposed to do? Anyone have any ideas of what's like a good way to attempt to attack this question now? Hands are up. Francesco.
So I think we can do like a case by case basis and then add the two different cases. So like we know that for like let's say the bottom one, we know that it's 4 over 5 depending on the third digit. So we can have a case where the third digit is even and then a different case where the third digit is odd.
Yes. Okay. So what I'm seeing here, say again? So what I'm seeing here is it's almost like we're going to make a ginormous tree diagram that's going to go out this way. That is indeed one way to do it. See, because you're saying in order to make a decision of what happens here, I need to know whether this guy was even or odd. And there is a legitimate way to do this. You see, because if I went and insisted, I want an even here. If I really want an even here, how many choices are there? Well, there's 5 choices for even numbers, so it's 5. Oh, but then I need to take into account whether this guy was even or odd. I'm not saying this is wrong. I'm just saying this is a way of doing it, where you say, if I wanted to figure out how many ways I could end with an even there, well, I need to look back one of them. It's like prerequisites when you take classes. It's like, then okay, how do I know about this one? I need to go back one more. And so one legitimate way to solve this problem it could take a while, but one way to solve this problem is to say, look, I've got 4 digits here. And let's like count how many ways to do this, where I happen to have all of them even. Actually, I only need to worry about the first 3. Even, because the last one has to be even, right? So if I have even, and I'm just going to write the last one in green because it has to be even. This is one case. We're doing case by case. Let's do this one right away. Can anyone tell me how many ways can you make a 4-digit number where it's even, and no 2 equals next to each other? Like no 2 equal digits next to each other. This is actually doable. Braden.
We would have four options for the first because we could do only if the 5 is beside 0. And then the same goes for the second and the third and the fourth. So we just have 4 different.
Okay, and just to emphasize, what happened here was like, this was actually just 2, 4, 6, 8. That's the easiest one. But the second one is actually like slightly more complicated. It is 0, 2, 4, 6, 8, except not the first. Did that make sense? That's why that's a 4. That's a 4 because it was 5 choices except the first, and so on. And that would be one case. But there's another case, which is even, odd, even. Do you see how this is going? I would have like 8 cases actually. It's like all the different evennesses and oddnesses of the first 3 things. But just to show why this is doable, what's this one? Let's just do this one together quick. What do I multiply to get this one? Sydney.
So it'd be similar as the last one, except for the tens digit, you would have 5 instead of 4.
Wonderful. Oh, actually, I think I can do better than that. I'm just looking at it slowly because I'm like, I haven't thought this through yet. So let's go to this 5. This is 5 because...
Oh, and the last one is also 5.
Yeah, and the last one's also 5, right? That's nice. Because you see, I've got a full 5 choices here. Odd number. Of course it's not going to be equal to the even number, right? So I've got full 5 choices. No conflict. This one is 1, 3, 5, 7, 9 with no conflict with the previous. By the way, this is also showing why it's useful to think of an order that we're going through, because we can just say, do I have any conflict with any of my previous? And the even one at the end is also 5, because now you have no conflict with this odd number that's here. So I'm saying, like, Francesco, this would work. You could work this out, and in like 8 lines, I can do it, and I can add. Now, I put this question here because it's weird. Oh, Francesco, did you want to add something?
Yeah, I was just noting that I just have a slightly different way of looking, like essentially that way, but I started building from the third digit. And I'm still looking it up, but yeah, it's essentially the same idea.
Okay, cool. So if you started working from the third digit and worked the other way, you sort of make this tree diagram of what I depend on. So I think what I just did is I just kind of inflated your whole tree diagram in one shot. But I'm saying that those ideas are all like in the same space. What I want to do with the last few minutes is to move us to a totally different space. And my goal of doing this as the first day in the Combinatorics class is to give an idea of the fun part about combinatorics is that there are lots of ways to look at questions, and sometimes we can bring a different way of thinking about something and crack it. So when you look at a question like this, that is so frustrating, the first thing you do sometimes is to say, can we solve an easier question? What's a easier, smaller version of this, just to get our feeling for the for like what we're supposed to do? Can anyone suggest like an easier version of this question? 3 digits. Why are you so hard? Yeah. I'm just gonna go with 1 digit. Okay. Let's start like super easy. So let's see. Although the reason why some people might be saying what's up with the 1 digit is because what does it really mean to have a 1-digit number where I have no equal digits next to each other? It's like that doesn't happen. There's no equal digits. But it's okay. We can still start there. So what if we just ask the 1-digit version? Well, remember it has to be even. So that's easy. The number of 1-digit numbers which are even and don't start with a 0, that's just 4. Okay. So then that suggests that we should try the next problem. And I'll say the next problem is, yes, indeed, 2 digits. Thank you very much. Was that Ben? I just want to learn people's names. Yep, Ben-san, and also Sydney. So 2 digits. Okay, how do you do this? We don't have to be clever. We just want to find a pattern. Can anyone help me solve 2 digits? You don't have to be clever. The numbers are small enough. Even and no 2 digits next to each other which are same. Raise hand. Okay, I see that Ben, you had thrown an RH up.
Yeah, so the only 2 numbers that have that are even and have 2 digits next to each other are 0, 0, 2, 3, 4, 4, 6, 6, 8.
Bad. Okay, you're saying the bad ones, right?
Yeah.
Bad guys are 2, 2, right? 4, 4, 6, 6, 8, 8. Oh, no 0, 0, because it has to be 2 digit. Now what do you do with this?
Well, there's 50 even numbers that are 2 digits, and we know the bad numbers, and we also know like we can't have 2, 4, or 0, 2, 0, 4, 0, 6, 0, 8, and 0, 0. So we subtract those, and then we subtract bad numbers.
Okay, I get it. So you were going to go with like the total number of even things, like combination lock type things with 2 digits, and you also wanted to subtract out the one starting with 0. That works. I'll just write that down. So total, like, well,
I don't think there's 50 even numbers, so because 100 isn't.
so this is complicated, right? Because it's like, how would you deal with that? Because like there's 0, 0 also. So just to save some time, because we're close to the wire on the end of the course, sorry, not the end of the course, end of the day, but there's a slightly easier way to save this a bit. It's like, how many even legitimate 2-digit numbers are there? Legitimate means not starting with a 0. We can do that one straight. Total even 2-digit. If I have 2 digits, you know what? Let's get someone else on this, just because you've gotten this a long way, and let's just finish this off with somebody else jumping in. Sydney?
So the last digit can be any digits, and the first digit can just be anything as well.
So there's 5 choices. And the first digit is anything that is not 0. Because this is total even. We don't care about same digits next to each other. So it's 45. Actually, it's quite satisfying. The number of 2-digit numbers. How many 2-digit numbers are there? 90. Is that okay? Like from 10 to 99. There's 90 of them. Are you surprised to find out that there are 45 that are even? Not really. That's half of them. Okay, so there's 45 over here. So this is 45. This is 4. If I combine them, then the answer to the question of how many 2-digit numbers are there, no 2 equal digits next to each other, and even, is 45 minus 4, which is 41. It is at this point that you get very scared. You should get very scared. What kind of a number is 41? If I was hoping to look for a pattern, oh no, it's prime. So if it's prime, my answer is not going to be something times something times something, because where does the 41 come from? Actually, I once talked to a famous combinatorialist who pointed out that when you're trying to guess formulas for things, it's really useful to prime factorize the answers for small values. If you prime factorize them and you see small primes, then there's probably something to do with factorials or chooses. If you see big primes, you know you're out of luck. 41, ouch. Okay, that's really too bad. But I want to do something a little bit different. That's the number of even ones, okay? How many odd ones are there? Remember, I'm still asking the same kind of question. No 2 equal digits next to each other. But now I want odd. What's it for the first one? 1 digit. Uh-oh, did something happen? Oh, wait. What is, oh, wait? Okay, Brayden.
We just have 5.
5. Because it's like, yeah, 1, 3, 5, 7, 9. How about this second one? What's the deal here? How many odd ones are there? How would we do this? Okay, so Charlie?
So you can do the same process where there's 45, so like 9 times 5 total odd numbers. But then there are actually 5 bad numbers, 11, 33, 55, 77, 99. So that means there are 40 that work.
Okay, that's 40. That's kind of interesting. All right, now, why did I do this? I did this because it's like, I guess there's not a pattern of multiplying. Does anyone else see something that's kind of nifty? Francesco.
So essentially, if you add them together, like the variable, even and odds, you get a factor.
If you add them together, you get a...
Like 40 plus 41 is 87.
Oh, yes.
Do the 1 digit, you do 4 plus 5, like the odds plus 2, you get 1. So the total number of viable even and odds together is 9 to the power of 9.
Okay, so we found out that if you add the two together, you get a power of 9. That's right. And actually, that makes sense because that's what we did at the beginning. At the beginning, we were like, how many of these no two things equal next to each other? Okay. Can anyone see anything special about how these, like, the 4 and the 41 come out? Anything that feels like poetically right? Consecutive numbers. Okay, and 这下. Okay, you subtract the number of this first one from the total to get the second one. That's true. And they're also consecutive. And let's get Brandon. Brandon, do you have a thought?
Well, it's like 9 to the power, it always has one more than the even is missing. Normally you would divide it by 2. One of them is a negative number, you have to give one.
Okay, I heard that something about divide by 2, right? Because it's like, come on, how many of them are even? Like half of them. Well, actually, that feels pretty lucky, by the way. When I came upon this problem, I was like, no way, really? It's just off by 1? How can that be? Like, I wouldn't have expected that to happen. That feels too coincidental. How do we prove that? Well, in order to prove that, we actually need to go and figure out some other way to try to count this. Because it's too painful to try to do this all the way through. I mean, when I say do this all the way through, it's like, what if I had 3 digits? Then I have to do all this funny subtraction. But I have another way of thinking of this. You can start to build the answer for the next number of digits using the answer for the previous number of digits. How might that be? So let's suppose we're going to define some sequences now. Suppose I have En, which is the number of even n-digit numbers with no equal digits next to each other. And let's do the same for O. That's not a 0, that's an O. The number of odd n-digit numbers, no two equal, next to each other. Why did I write that out? I wrote that out because one of the basic principles is something called recursion. This is like a more sophisticated way to count things or to do other complicated things. My claim is that you can actually write En plus 1 in terms of the answer for En and for On. And that's actually one of the key points here. And that's related to things we saw today. The things we saw today were, suppose I have an n plus 1 digit number. So suppose, well, let's just do it like this. Yeah, let's do this. I'm going to draw like, imagine we were doing 5. This is very general now. Suppose you have your first n digits and you have your last one. And suppose what you want is you want this one to be even. Okay. Can anyone tell me why it might be useful to know En and On if I want to know how many ways I can finish this up and get an n plus 1 digit number ending in even? Aha. Shanai?
If like you're playing with like the first n many digits and you know that last digit becomes the tens digit of like the next number of numbers in the sequence, then you can case on whether the last digit is even, and in that case you know how many ways you can have the last digit be even and not duplicate the previous one, which is just 4. And if it's odd, then it's 5 because the even and odd can't lose.
That's the key. Did that make sense to people? If I had a number which had n digits and ended in an even, how do I finish it? I have to choose an even digit that doesn't match what's next to it. That's why I lose one option. These are the things we were thinking about, right? Remember, it was like times 4 or times 5. And how it depends is it depends on what that was ending in. And so, like, the 4 is just because you must avoid the even next to it. But the beautiful thing about the odd next to it is times 5. I mean, you're not going to have to avoid anything. These are 0, 2, 4, 6, 8. So what that means is En plus 1 is going to be the number of even n-digit numbers times 4 plus the number of odd n-digit numbers times 5. Okay? That's going to be the heart of trying to figure out why this proof works. to prove why this interesting pattern works. And just to finish today's class, I just want to work out, the answer for the 4 digits using this recursion idea. So the number of even things is this. Okay, so it's 4 times the previous even plus 5 times the previous odd. So what did we have? We had n, we had en, which is the number of even things, on, and I'm even going to write the total. So when n was 1, even was 4, odd was 5, the total was 9. I'm just remembering what we had. When n was 2, the even was 41, the odd was 40, and the total was 9 squared. Okay? Now we can keep going. Then for n equals 3, what was the formula? Let's write it again. En plus 1 is equal to, it was actually 4en, 4 times en, plus 5 times on. That's not a 0, that's an O. So let's do the math. Oh, this is hard. 4 times the even. So that's like 164. Oh, I can add 5 times 40. That's easy. 5 times 40 is 200. So I think it's 364. I hope. If it's, please correct me if I do arithmetic wrong. I'll do the total next. 9 cubed. I know. That's 729. Oh, I can subtract that. That's the number of days in a year. That's kind of cute. And if I keep going, I'll just do the last one. 4. 4. 9 to the 4th is the total. Oh no, I forgot what that was. Does anyone know what is 9 to the 4th? We should have enough people here who know the answer to this. I forgot. Ah, wow, you guys are good. 6561. Okay, 6561. And we have to do some actual calculator work. I do not intend to do this with my hands. Is anyone able to quickly do 4 times the 364 plus 5 times the 365? And what is it? It's 3281. And 3280. And now we have the chart. And now we know the answer. The answer is 3281. But more importantly, this question wasn't interesting just because it had an answer. It's interesting because there's a beautiful pattern. What do you think is the answer here? Or the answer meaning what the heck is going on in this problem? Anyone want to share? What do you think is the general form? Raise hand, Venkatesh.
Is it basically just like 9 to the power n over 2 and let's see when 4?
Yes. It's like 9 to the power n over 2, roughly, rounded. Okay, any pattern on the rounding? Does it always round up? Does it always round down? It alternates, alternating. Actually, there's even a way to write that down as an explicit formula. Whenever you do alternating rounding going up and down, the way to do that is by adding powers of -1. Because -1 to even numbers is +1, -1 to odd powers is -1. So actually, the exact formula is something like 9 to the n. I forgot if it's plus or if it's minus, -1 to the n, divided by 2. The way I always do this is I write that down first, and I stare at it, and I see, is that right, or am I off by a sign? Oh, that is so cool. Yes, that is what I thought when I came upon this. So is it plus or is it minus? I forgot. Ooh, it doesn't look like plus to me. Oh, yes, it is. It's plus. It's okay. I think this is okay. I think this is okay because I'm just checking it with like the first one, right? With the first one, it's like 9 to the 1 plus -1. So you're going to round down. When you plus the -1, you round down for the evens. Perfect. And then for the next one, it's rounding up. And that's because -1 squared is positive. So that's the answer. This thing. It's not a big multiplication. It's actually a rounding. And we'll talk about like next class about like why is this true? Why does this even work? There's a lot inside here. And hopefully this is a good introduction to what the flavor of this course is going to be. I always want to make sure the course teaches the basic ideas, like the multiplication principle. That's what today's lecture was. But does it in a way where you get to see like all these other weird stuff. This is actually a fact I just discovered myself when I was like making problems for people. And I was like, no way. It's just off by 1. That's so cool. And I had to teach it. Okay, see you guys next time. Bye-bye.
Thank you.
Oh, sure.